Section 7.3 of this chapter is entitled Reaction Stoichiometry. And stoichiometry is a fancy name that I will never make you spell, by the way, because it's kind of weird. But it's basically the study of quantitative aspects of chemical reactions, which is really related to amounts, like how much do I need to make this much, etc., etc. So stoichiometry is really the study of measurements and how much you need to make something happen. So in chemistry, what's really important here is that we use stoichiometry in relationship to the conservation of matter, which just says that all matter that goes in has to equal the matter that goes out. You can't lose or destroy or create, for that matter, any matter. It has to be accounted for. And we use the balanced chemical equation to figure that out. So in the lower right-hand corner there, that's a balanced reaction, which we talked about at the end of Chemistry 221. In that reaction, we're taking two solid pieces of aluminum and reacting it with three gaseous pieces of bromine, Br2, to make two solid pieces of aluminum bromide, AlBr3. The 2, the 3, and the 2 are called the stoichiometric coefficients. They tell you relative amounts. Now, I use pieces and things like that in the last description. You probably know that this is going to be the mole in chemistry. So in chemistry, we would say that you need 2 moles of aluminum to react with 3 moles of bromine, and that will create 2 moles of aluminum bromide. Notice that 2 plus 3 on the left side do not equal 2 on the right side. The big stoichiometric coefficients do not equal each other on the other side. But what does equal, and what's important, is that the left-hand side has 2 aluminum atoms and the right-hand side has 2 aluminum atoms. And the left-hand side has 3 times 2, 6 bromine atoms, and the right-hand side has 2 times 3, 6 bromine atoms. So the atoms are balanced, even though the stoichiometric coefficients may or may not be balanced, and that's something to remember. Also, instead of calling it left and right, let's call it by the official names. The left-hand side are the reactants, and the right-hand side are products. And those little things in parentheses to the right of the chemicals, those are the states of matter. They're not always included, but they can be very helpful. S means solid, G means gas. You'll also sometimes see L for liquid, and also you might see AQ for solutions. So that's kind of a very fast overview of a lot of the last chapter of Chemistry 221, and we'll talk about it more here coming up. As always, if you have questions on anything from Chem 221, because I know that was so long ago now. No sarcasm. Honestly, I kind of feel that way myself sometimes when I'm starting a new term. But anyway, that's a personal problem. You don't need to worry about it. Oops, I'm recording it. Okay. Anyway, if you ever do have questions on anything, I'm happy to help you. Okay. Don't lose any sleep about it. There are no dumb questions in my class. Some of my answers, you may need to ask the question again to get a good response, but your questions are valuable to me and I'll do my best to answer them. Chemistry is kind of like cooking. A chemical reaction is kind of like the recipe up there at the top middle kind of to make a pancake. And you can see that it says a cup of mix and 3/4 milk and an egg makes 8 pancakes. All right. Woohoo. Well, if you're hungry, that can be really important. In the lower left-hand corner, there's like another recipe of sorts where you have flour and sugar and oil and chocolate and eggs, and somehow that makes a cake. Fantastic. You can cook just about anything if you put your heart to it. And in chemistry, you can make just about anything too, as long as you follow the instructions. So you do need to know how much to add. So for example, in your cake, if you had too much flour, it wouldn't come out very nice. On the other hand, you added too little flour and it would come out kind of weird and hard and stuff like that. So you have to know the amounts and stuff in cooking, and you have to know the amounts in chemistry. If you're having people over for dinner, it's nice to know how much you're going to make. So if you're making one cake and you have, say, 6 people or something, 8 people, I don't know, that would be fine. But if you have 20 people coming over, you might need, for example, 2 cakes. So it's nice to know how much you're going to make, how much you need to put in. In chemistry, in addition, that doesn't usually happen in the kitchen, but it can be. Chemistry can be dangerous, all right? You can have an excess amount of energy released, or all kinds of things can happen. So there's a lot of reasons for paying attention to a recipe. There's a lot of reasons for paying attention to something in the chemistry lab. And this is what we're going to try and conquer in this section. So this is a flashback to Chemistry 221, and I want to talk about the important ingredients in a chemical reaction. And this is another example of a chemical reaction. This is aluminum and oxygen making aluminum oxide. So you can see, first of all, that there are some diatomics. Aluminum is not a diatomic, but oxygen is, so that's why it gets a little 2 next to it. And also, those stoichiometric coefficients, really cool. And again, 4 plus 3 does not equal 2. That's okay. But the atoms of aluminum on the reactant left side equal the atoms of aluminum on the product right side, and the atoms of oxygen, 3 times 2, 6, equal the atoms of oxygen, 2 times 3, 6, on both sides. So it's the atoms that are balanced, but not necessarily the coefficients. Those coefficients are super important, though, we're going to see in a little bit, so just hang on. You might see, like I said earlier, solid, gas, aqueous, and liquid. Those stand for the states of matter. They're not always there, but it can be really helpful. And again, it's not the coefficients that are balanced, but it's the atoms that are balanced. This is the law of conservation of matter, sometimes called law of mass action. And you've got to pay attention to that if you're going to have any success in the things we're going to talk about here shortly. Now, for this reaction where 4 aluminums react with 3 oxygens to make 2 Al2O3s, that reaction implies all of the following ratios. And there's a whole bunch of them. So let's talk about the first couple ones. In the upper left-hand corner, it says 4 moles of aluminum for every 3 moles of oxygen. And it's not like magic where this all came from. The 4 came from right there by the 4. That's the 4 moles of aluminum. And the 3 in the bottom is the 3 right there, 3 moles of oxygen. No problem. So you can see the one right to the right, 4 moles of aluminum, 2 moles Al2O3. You can see where that ratio comes from. But sometimes it's nice to have the opposite ratio. So let's flip the 4 moles Al for every 3 moles O2. We would then write it 3 moles O2 for every 4 moles Al, etc., etc. So from this reaction, we get those 6 ratios, and those ratios are really, really important. It's a stoichiometric ratio between reactants and products, products and reactants, reactants, reactants. Anything is possible, but it comes from the power of the balanced reaction. Like all good conversion factors in dimensional analysis, you can flip them on their head. So you don't want 4 moles aluminum over 3 moles O2. You can flip it, 3 moles O2 over 4 moles Al, no problem. That's where these ratios become so important to chemists, because it allows you to go from one reactant to another, from a reactant to a product, from a product to a reactant, or a product to a product. And I'll show you some examples of this here coming up. Here's a reaction. Let's say that we have nitrogen and hydrogen reacting to make ammonia, NH3, and we're mixing 10 moles of H2 with an excess of nitrogen. What stoichiometric factor would we use to calculate the moles of NH3 produced? Okay, so in the naming of this, in the language of this problem, it says 10 moles of H2 with an excess of N2. So that means we have more N2 around than we know what to do with. So we're going to try and convert, in this case then, moles of hydrogen into moles of ammonia. So we're starting with 10 moles of hydrogen. That's like the top part. So we could write 10.0 moles of hydrogen. And we want to convert this into moles of NH3. So by the H2 there's a 3. So I'm going to put 3 moles H2 on the bottom. And we want to turn it into ammonia. There's a 2 right there, 2 moles NH3. So the ratio we're going to use here then is the bottom one. It's 2 moles NH3 for every 3 moles H2. Now I hope you're kind of seeing here what's going on. We're going to want to convert how much hydrogen we have into how much ammonia we can create. And you can see hopefully here how the moles of H2 on the top and the moles of H2 on the bottom are going to cancel. That's going to allow us to calculate the moles of NH3 that we can create. So in this problem, if we would multiply 10 moles by 2 over 3, we would get 6.7 or whatever. That would be the moles of NH3 that we can get from this reaction. So that's where these stoichiometric coefficient factors come in, and that's where having a balanced equation so important for chemistry. So here's another kind of question you might see. It says, what mass of sodium hydroxide would be required to produce 16 grams of magnesium hydroxide by the following precipitation reaction? Okay, so this is another little thing we talked about in Chem 221 at the end. A precipitation reaction is a type of reaction where the like parts are trading places. So magnesium and sodium are both positive metals, cations. They're going to swap places. Now magnesium was positive 2 on the reactant side, and it's going to be positive 2 on the product side. And if it's going to start dancing with hydroxide, which is a -1 polyatomic ion, the formula then will be MgOH2. Now in the process, Na is going to start dancing with chloride to make NaCl. We'll balance the atoms and put a 2 in front of the NaOH and a 2 in front of the NaCl and be good to go. But also what we can do here, most hydroxides are insoluble. So that means we need to put an S by them. The only time we do is when the hydroxide is next to sodium, potassium, lithium, the group 1A cations. No problem. And chlorides are usually AQ. Sodium is always AQ. So that's why there's the 2 there by the NaCl. So again, if you have questions on this, let me know. But what we're going to do here, we want to figure out how much sodium hydroxide, NaOH, we need to produce 16 grams of magnesium hydroxide. And what the balanced reaction is going to give us, it's going to give us a mole ratio between MgOH2 and NaOH. So if we can turn the grams of MgOH2 into moles, we can then use the balanced equation ratio to go from moles of MgOH2 to NaOH, and then finally, since we want mass, which is grams, we'll turn the moles of NaOH into grams using the molar mass and be good to go. So let's see what this looks like then mathematically. So we're going to start in this case with 16 grams MgOH2, and we need to turn that number into moles of MgOH2. Now that 58.3 number is the molar mass of MgOH2. If you take a magnesium, which I think is like 24.3, and add oxygen about 16 and hydrogen, which is about 1.0, you're going to get 58.3 grams per mole to the 10th position. And that allows us to go from grams to moles of MgOH2. But the new part now is this in the middle. And this is that ratio I was talking about. There's an invisible 1 by the MgOH2. Chemists don't usually put 1s. They'll put 2 and greater. 1 mole magnesium hydroxide needs 2 moles NaOH. That's where the ratio came from. And that allows us to turn the MgOH2 into NaOH. Finally, then, we're going to turn moles of NaOH into grams using the molar mass, add up a sodium, an oxygen, and a hydrogen, and it's about 40.0 grams per mole. 2 significant figures is what we want right here because we put 2 sig figs in, 22 grams NaOH. Now imagine the power of this just for a second. Your boss says, hey, we need 16 grams MgOH2. How much NaOH do we need? You just calculated 22 grams, and that's what you can tell your boss, and that's what will allow you to get the 16 grams out, which is kind of cool. So I call this sometimes the grams, moles, grams dance. It's not really a dance, but it kind of feels like it. And what you're doing, you're turning grams of your starting material into moles, like we did MgOH2. The moles to moles part comes from the balanced reaction, which you just need to balance and figure out. And then you go back to grams, the moles to grams part, using the molar mass of what you're looking for. We'll do this a lot. It's not hard or anything like that. Make sure you're hip how to get a molar mass value from the periodic tables, and you're good to go.